Good morning, everyone. People are still sitting. Thank you all for coming. I'm so excited to be here. I hope you're enjoying the nice weather in Amsterdam. It's my first time presenting in the church, so God bless JavaScript, your code, and my presentation. All right, let's get started. For those of you who don't know, we recently released a brand new progressive web app. It's a brand new code base, and we did it in 11 weeks only. So that's what I'll be talking today about, and a little bit about myself. My name is Imad Elyafi, and I'm a software engineer on web core experience team at Pinterest. Before Pinterest, I was at Facebook and at Yandex and some other companies. If you have any questions, please make a note, and I'll be happy to answer them in the end. So the presentation consists of three main parts, and the first part is the story behind our old mobile web, and I'll be talking about how we got to the point that we had to rebuild our mobile web experience from scratch. The second part is technical implementation, and I'll be talking about all the technologies that we use, performance optimizations, and other things that under the hood of our progressive web app. And in the end, I will share with you the numbers and the results, so hopefully you can use this information to present at your team and convince people in your company to invest more into mobile web. First of all, let's take a look at our old mobile web experience. And we took a look at our old mobile web experience 3 years ago, and we realized that it's broken. At the time, we knew that native apps producing up to 80% higher engagement, so we made a tough decision to push our users through interstitials or popovers to use native apps. And let's say you want to see pictures of cats, so you go on Google, you search for cats, you click on the link, and if you don't have an app, if you navigate to Pinterest, and if you don't have an app, then you would see this thing on the screenshot. And if you click on it, you'll be navigated to the App Store. In the worst case, after registering, you won't see pictures of cats. So experience wasn't great. And we know that we maybe upset some users, but we truly believe that for the size of the team at that moment, it was the right decision to support 3 platforms instead of 4. But we are much bigger now, and we're ready for an upgrade. So at Pinterest, we run a bunch of experiments before we ship any UI changes. And while our experiment metrics showed us that pushing people to native apps produced higher engagement and overall, we didn't measure the sentiment cost. We didn't measure what we're missing or what we're losing. Because in fact, if a person had a bad taste in their mouth after first experience visiting Pinterest.com from Google search results pages, they just don't want to come back. And we can't measure this. So the lesson learned, be aware of compounding sentiment cost of aggressive growth strategies. So we came to a fork on the road. Do we encourage people to continue to use native apps? Or do we invest into mobile web? And thanks to one of our team members who started it as a Makeathon project, who built a Pinterest feed which was as fast and as nice as a native app, we decided to prove that investing into mobile web worth it. But some of you may ask, what are the other reasons for that? And first of all, people in many countries, they still have to pay for the internet connection per megabit basis. In California and Europe, we have pretty reliable and fast internet connection and pretty fast hardware. And people in some countries, they can't afford or don't want to download a native app. So having lightweight mobile web experience can capture all these users. Another thing is, if you have a lightweight and mobile web experience, then you have an opportunity to capture these low-engaged users and convert them to high-engaged users. And lastly, if you have fast and reliable mobile web, then your SEO results will be much better. And this one is pretty obvious. one of the mostly commonly asked questions was, should I build my website responsive, or should I build a separate website? And about 5 years ago, there was a huge push for responsive websites where your web app should be working perfectly across different platforms and size screens. And the answer is, if you have a team at least of 20 people, then you should definitely invest into mobile web. You can see the reasons for that. And first of all, if you have a single app that combines desktop and mobile version, then whenever your engineers will be making changes to the desktop version, they will be testing it on desktop Chrome only. Unlikely they will be testing it on Android devices or some mobile devices. So this will lead to a bunch of new bugs, which you really want to avoid. Another thing, if you have the same code base, you end up with having such low logic forks like if desktop, if mobile, then you do something for one platform or another, which immediately goes out of control and increases the logical complexity of your code. Also, by not having a lightweight mobile web experience, you're losing an opportunity to test assumptions for this target audience, which are people with slower internet connections and slower hardware. And in the end, responsive design works better for websites, something like news website or a website where you have a bunch of text and some pictures. So it's much easier to reflow and adopt this design into touch screens or smaller devices. While Pinterest is an app, meaning like you can change boards, you can save pins, even send messages, and so on and so forth. So every single feature works much better when it's designed for a specific platform. And since we decided to build a whole new web app from scratch, now we can think how can we approach the problem. And a year ago, when I was presenting about React migration, I was advocating for an incremental approach where you rebuild your website piece by piece, page by page, feature by feature. But with the mobile web, we decided to do the opposite. And there is two reasons for that. First of all, as I mentioned before, we didn't invest that much into our old mobile web. So it was much easier to do a code freeze. And the second reason, we were building a brand new website which shares very little to nothing with the old one, meaning there is no reason for us to start on the old code base. So this was the story, and now we're moving towards technical part. And in the heart of our new mobile web experience, we have progressive web app technology, which is a new software development methodology which denotes a term that combines the best out of websites and native apps. It's just that web app that has taken all the right vitamins from the native apps to perform and act like a normal app downloaded from the Play Store or the App Store. On this slide, you can see some of the features of PWA. And the main one, probably, of course, the app shell. It's the skeleton of your app. It's the minimal set of CSS, JavaScript, and HTML that is required to render content inside of the frame. And it's a very powerful pattern that, when it's used in combination with the service workers, can provide you significant performance improvements. And I'll be talking more about it, and I'll share the numbers with you. Like in the native apps, you can prompt user to send push notifications. Also, with the app shell and service workers, now you can provide meaningful offline experience. And this was not the exhaustive list of the features. And even this list is not exhaustive. We're already using background sync API, credentials management API. But there is a lot of more, like access to camera hardware, device memory, and of course, you can open the native share prompt. And all of this is possible because of the service workers. And before we'll be talking about our implementation of PWA, let me give you a very high-level overview of service workers. How many of you have used service workers before? Pretty good. I can see a lot of hands. How many of you have written a service worker before? Less. All right. Service worker is a script that stands between your browser.js and the network, and among many other capabilities, it can capture requests and response and respond to it in different ways. And now let's take a look at the lifecycle of the service worker. And first of all, we have to register service worker. And normally, we would do it on window onload event, where we put the URL to our service worker. And this is actually the actual URL of Pinterest service worker, so you can go online and check it out if you want. So after starting registration, service worker will fire a couple of events. The first one will be install event. This is normally a good time to pre-cache all the critical assets, for example, JavaScript that is needed to render your app. If installation went successfully, we will go to activation step, and this is a good time for you to clean up some caches and do some sort of cleanup work. Since service worker is a special type of web worker, you can send a post message, so you can communicate between browser.js and service worker. And now, this is where the power of service workers comes from. If you remember, I mentioned to you that service worker is a proxy that stands between your browser.js and the network. So service worker can capture requests and do different things to them. For example, here we can see the cache first setup. Basically, we try to retrieve some asset from the cache, and if cache is missing, then we'll go to the network. So just to recap, service worker is a proxy between your browser.js and network. It can capture requests. It can respond to them in different ways. And in order to start using service worker, you have to register it, go through installation and activation step. Now let's take a look how our Pinterest web app works, starting from the point when you type in pinterest.com in your mobile browser, and we go to our servers. And by the way, we're using a library called Workbox for dealing with service workers. It just makes your life easier, but you can achieve the same results with the native API. So browser sends a request, things happening in the normal flow. We're getting an HTML response. And in the normal flow, we do HTML parsing, JavaScript executing, spawn additional requests, and so on and so forth. And on window onload, we would call register service worker. So this time, our service worker will go through installation and activation step. And during installation step, we would aggressively pre-cache all of our critical resources. That's what would you normally put in the head tag, whatever is critical for your app initialization. Then, during activation step, we would set up cache-first strategy for the rest of the resources. And we would also pre-cache the app shell, which will be used in future page reloads, and I'll be talking more about it. So worth to note, there's two types of caching. First one is aggressive pre-caching of critical resources, and the second one is cache on the go, that I'll be talking more about it. And also another cool thing, if you're using accelerated mobile pages, then you can pre-install your service worker from an AMP page. So by the time when user comes to your website, everything will be already in cache, and your loading times will be super fast. Pretty cool, isn't it? And here we can see how the caching on the fly works. Let's say a user decided to go to the profile page, and we want to get JavaScript asset for the profile page. Then we send a request. Service worker will capture the request. We'll check if we have this asset in the cache. And if not, we'll go to our CDN and retrieve the asset. So this was the first page load. Now let's take a look what happens when we revisit Pinterest.com. And first of all, we don't have server-side rendering in favor of app shell. The metrics showed that it works better for our users. It provides less logical complexity and reduces loads on the servers. And during the explanation of the first page visit, I very briefly mentioned that we do pre-cache of the app shell. And page reloads and revisits is the time when the app shell goes into play. So let's say we navigated to Pinterest.com again. Our service worker will send back the app shell from the cache. So we don't send a request to the server at all. And since the app shell is similar to the server-side response, it contains whatever the normal response would be, like HTML, JavaScript, CSS, and some initial data. So it would parse this HTML and execute and do normal things in the normal flow and will spawn a bunch of additional requests. But the only difference is we already have everything in cache. So all these requests won't go to the server, and the service worker will send us back all the assets from the cache. So that's why page reloads will be much faster, and I'll be sharing with you the numbers later. And since we're dealing with an app, we can update the app version. And some of you may ask, how would we do it? And let's say we're using Pinterest.com, and we want to save a pin. So we send an API request. The service worker will bypass the request because we want always have the fresh data from the API, so we don't cache API requests. And once we get a response from the server, we can see that the response contains the normal data related to the response, but it also contains some sort of client context, which is the app version and some additional data like experiments or the data related to some initial state data. So browser will check the app version, and if the app version is the same, we don't have to update the app. But here's one thing that we're doing here. If you remember, I mentioned that we aggressively pre-caching the app shell, and it contains the initial state information that is required to initialize the app. But what if, after using Pinterest, we updated this information? Let's say some user data or experiments, or it could be something else. So in this case, we want to refresh this data, and there is two ways of doing it. The first one, we can remove app shell from the cache and recache it again. But this is an expensive operation because these changes can happen on every single API request. So instead, we would save all this additional initial state data in local storage. Thus, by the time when we reload Pinterest again, we would override the initial state in the app shell with the data from the local storage. And if we have the new version, then we want to update the app. So we call service worker update, and we go through the normal installation and activation steps. Just a couple of things to keep in mind. If you want your service worker to become active right away, you want to do two things. First of all, you want to call skip waiting during installation step. Thus, it will go to activation step right away. And you want to call client's claim inside of activation step in order to make the service worker active in all open tabs in your browser. And after that, on the next route change, we'll just do full page refresh in order to re-execute newly cached JavaScript files. How are we doing so far, so good? And because of the service workers, we got another cool optimization for free. The service workers cache is much faster than the regular cache, meaning we would skip some parsing and compilation time. In this particular example, we would save 30% or 300 milliseconds on the main bundle, which is pretty cool, I think. And as a result of service worker caching, we can provide meaningful offline experience. Let's say we open Pinterest.com, we're clicking around. Now we're turning off the internet connection. Navigation is still there. Everything works. And now we turn off connection and reloaded the page. It's still working, even though we didn't show any pins but we're already running experiments to show the unseen pins from the previous visits. So meaning the offline experience lets you to test more assumptions and gives you opportunities to other new experiments, which is pretty cool, I think. Now let's talk a little bit about performance. And it's not a secret that the JavaScript size is one of the biggest bottlenecks of your website loading times. And for that reason, we decided to do some sort of smart bundling, meaning getting a web page to get load and get interactive quickly benefits only from loading the code that user needs upfront, because we would skip some network, parsing, and compilation times, and other expensive operations. And the rest of the code can be loaded as needed. So we're using Webpack for bundling. It works well for our needs. And we started with breaking the bundles chunks into 3 different types of chunks. The first one is vendor chunk, where we pack all the third-party libraries. The second one is entry chunk, where we combine all the critical JavaScript and shared libraries across Pinterest. And the last one is an async chunk. We have many chunks like that that are related to specific routes. So basically, it's the code that is necessary for rendering each specific page. On this slide, you can see a React router-based code splitting. And this is an example of close-up page. So at the very top, you probably noticed there is an import statement with the round brackets, meaning that it's a dynamic import in ES7, meaning Webpack will combine all this code into a separate bundle and generate an async chunk. Also, you probably noticed there is a comment says Webpack chunk name, which is used for service workers caching. Because before, we had to deal with all these constantly changing hashes, but now we can use regular expressions, and we can filter requests based on that, which makes our life much easier. Now we can take a look at the network waterfall. So this waterfall highlights how progressively loading code shifts the necessity from huge monoliths, megabyte-sized bundles, towards all these 4 different types of chunks that we have now. And at the very top, you can see how we loaded our very first critical resources. And after that, we can see that user went to home page. So we loaded home page chunk. Then we navigated to close-up page, explore page, and search page. So we can see how progressively loaded code helps us with that. And now you can see how the Webpack bundle analyzer helped us to visualize the problem. You can see there is 2 main chunks on the left side and a bunch of async chunks, which are relatively big, meaning that there is a lot of redundant code and repetitive code, which hurts our performance. But we can do much better. So this is how it looks like after applying all the optimizations that we had before. You can see that async chunks decreased a lot, and actually most of them decreased by 90%, and in the end, all of them are less than 3 kilobytes. And we did it in favor of a slightly larger entry chunk, which was increased by 20%. And now we can take a look at the loading times, what happened after we applied all these optimizations and service workers. So this is the numbers for the old website on slow 3G connection and average Android hardware, where we can see that users almost always had to wait up to 23 seconds before the website was interactive, which is pretty bad. But we can do much better. And the new mobile web is a drastic improvement. As you can see, we decreased the loading times from 23 to 5.6 seconds. And this is on slow 3G network and average Android hardware. On page revisits, the situation is even better. The time to interactive is down to 3.9 seconds, thanks to service workers and the app show and all these optimizations that I mentioned before. I'll probably skip this part. So we talked a lot about our major features and optimizations, but there is a lot of more that makes our mobile web experience so awesome and so cool. And I want to mention these little things that I'm very excited about. One of the cool features is that we optimistically update our UI, so meaning that our users, they don't have to wait until the response comes back before our UI is updated. Because of that, things like the navbar has immediate response and fill, which is pretty cool. Another cool thing is we created tap area component, which handles all the touch optimizations and providing at the same time first-class accessibility. Playing around the website, you may notice there is a compressed state on each of the navbar icons, meaning that you're actually doing something. So it basically is sending you a message that you're clicking on something. There is also optional compressed state item for things like pins. And in the middle, you can see pull to refresh optimization that gives you that native feel. The core of Pinterest is a grid of pins, and for that reason, we created a highly optimized grid component, which has inbuilt virtualization and would lazy load future images that gives you ability to have smooth scrolling for thousands of pins and images, and providing you truly infinite experience. Another cool little feature is helping for perceived performance, and we would show the dominant color placeholder while you're waiting for the images to be loaded. Now let's go to the results. We already saw that our website is much faster, looks better, but what the numbers would tell us. And instead of many words, let me show you this video, where you can see how much we can do for the 17 seconds that we spent on loading the old mobile web on the left side, and while we're using the new mobile web. Pretty cool. These numbers speak for themselves. 40, 50, 60% engagement improvements. This one I call impressive impressions graph. You can obviously see when we ship the new mobile web. This is the performance metrics that I mentioned to you before. And this is some of the engagement metrics. And important to note that we've seen almost zero, very little to zero cannibalization from the native apps, meaning that we were generating new engagement. And lastly, the hardest lesson was to convince people to understand that we don't have to push people to the native apps. But they were saying, but we know that the native apps performs better. No, you know that the native apps perform better than the old decrypted version. Thank you.